Good morning. Today we will learn about the difference between DTFT and DFT and also about the development of DFT from DTFT. Okay. Now in your syllabus this difference is not there, but I am giving you this because sometimes they may ask a question like compare between DTFT and DFT. So this may become useful. So please study this difference between DTFT and DFT, and after that we will go to the topic of the day, which is the development of DFT from DTFT. Okay. So straight away we'll go to the differences. So the first difference between DTFT and DFT is in its expression itself. That see, DTFT is represented by x of e raised to j omega equal to summation over n from minus infinity to plus infinity x of n e raised to minus j omega n, whereas DFT is represented as x of k is equal to summation from n equal to 0 to n minus 1 x of n e raised to minus j 2 pi k by n where k equal to 0 to n minus 1. So here we can note that in DTFT the summation is over from n equal to minus infinity to plus infinity, whereas in DFT the limit is finite, that is from n equal to 0 to n minus 1, whereas in DTFT the limit is infinite. Okay, so each of these terms I have explained earlier, so I am not repeating it again. Now about DTFT, it is a continuous function of omega. Omega means frequency, so DTFT is a continuous function of frequency, whereas DFT is a discrete function of frequency. Now in DTFT sampling is performed only in time domain, whereas in DFT we can perform sampling both in time and frequency domains. Now DTFT, it is a continuous infinite sequence where x of n is a discrete time signal, whereas in DFT it is a finite non-continuous discrete sequence. DTFT is periodic, whereas DFT is not periodic. Now, as already said, DTFT is calculated over an infinite summation, that is from minus infinity to plus infinity, which I have already told you by showing those expressions, and this means that it is a continuous signal, whereas DFT is calculated over a finite sequence of values, that is we have seen that it is calculated over summation from n equal to 0 to n minus 1. This means that DFT, the result is non-continuous. Okay, now in DTFT the omega in the exponential function, that is frequency, is a continuous one. Okay, whereas in DFT the continuous variable is replaced by finite number of sequences or finite number of frequencies located at 2 pi k by n ts. Ts is a sampling rate, or in other words we can say that the DTFT signal, if we have a signal, then we take the DTFT signal and then we sample it in the frequency domain at omega equal to 2 pi n, then what we get is will be the DFT of x of n. This means that if you have a signal x of n, then what we do is that first of all we take the DTFT of that signal and then we sample it in the frequency domain, not in the time domain but in the frequency domain at frequency omega equal to 2 pi n. Then what we get after the sampling of that DTFT signal will be the DTFT of that particular signal. So in summary we can say that DFT is just a sampled version of DTFT. So we are having a signal, we sample it in the frequency, we take the DFT, then we sample it in the frequency domain at omega equal to 2 pi n, and the output will be the DFT of that corresponding signal. So this is how DFT is developed from DTFT. Okay, but this we will learn more in detail just after this session. So we are going to learn more about this one, that is how DFT is developed from DTFT. Okay. So first of all, let us finish these differences. Then DTFT gives a high number of frequency components, whereas DFT gives a lower number of frequency components. DTFT is more accurate, whereas DFT, in order to improve the accuracy, we have to increase the number of samples to a very high value, and for that we need increased computational power. Then DTFT is defined from minus infinity to plus infinity, so naturally it can have both positive and negative values of frequencies, whereas DFT is defined from 0 to n minus 1, so it can have only positive frequencies. Now DTFT is only theoretical and it cannot be implemented practically, whereas DFT can be used practically, that is it is made use of in computers. So study these differences. I think these are very simple ones, so you can study the differences between DTFT and DFT. Now the topic for the day, that is how you can get DFT, or how development of DFT from DTFT. So the first sentence is a highlight, that is we sample or divide or split one time period of a DTFT at finite number of frequencies points, we get DFT. So this is how DFT is obtained from DTFT, that is by sampling at finite number of frequencies. That is, sampling is done in the frequency domain and the output will be a DFT. Now this is the explanation given. See, DFT maps one infinite and periodic sequence x of n with the period n in time domain to another infinite and periodic sequence x of k again with the period n in frequency domain. The meaning is that what is the function of DFT is that suppose that you have an infinite periodic sequence xn, okay, with the period n in time domain. Now this DFT, it maps, or that means it actually converts it into another infinite periodic sequence x of k with the same period in frequency domain. That is a conversion from frequency time domain to frequency domain. That is, using DFT we can convert an infinite periodic sequence x of n in time domain to an infinite periodic sequence x of k in frequency domain. So a conversion from time domain to frequency domain. This is what DFT does. Now if you want to convert it back, that is if you want to convert it from frequency domain to time domain, what we use is IDFT. IDFT is nothing but inverse DFT, inverse of the discrete Fourier transform. So if you have this DFT, that is x of k equal to summation from n equal to 0 to n minus 1 x of n e raised to minus j 2 pi n k by n, then IDFT or inverse DFT will be x of n. This will come here equal to 1 by n summation from k equal to 0 to n minus 1 x of k here e raised to j 2 pi n k by n. So x of k actually stands for DFT, representation for DFT, and IDFT will be x of n. So time domain to frequency domain DFT, and if you want to reverse it back we can use IDFT. Now next consider a finite length sequence x of n. Let that length of it be capital N. So you have a finite length sequence x of n and it is of length capital N. Now suppose that this sequence is appended with zeros infinitely on both the left and right. Appended means you are just extending that particular sequence towards both the left and right by adding zeros. Okay, that is called appending. Then suppose that you get the appended sequence as this. So you have a finite length sequence xn of length. Then now you are extending that signal towards both left and right. How? By adding zeros. Then you will get a sequence called appended sequence represented by x cap n, and it is given by x of n equal to x of n in the range n from 0 to n minus 1, and it will be 0 otherwise. Now this x of x cap n or the appended sequence will also have a DTFT given by x cap e raised to j omega. Why this cap? Because it is actually the DTFT of the appended sequence x cap n. So we write the DTFT also with a cap, that is x cap e raised to j omega, and it is given by summation from n from minus infinity to plus infinity x cap n e raised to minus j omega. And here x cap e raised to j omega is a z transform of s cap n, and it is evaluated on a unit circle z equal to e raised to j omega. Now we are going to sample, or we are going to split, or we are going to divide that DTFT, that is x cap e raised to j omega, at n equally spaced points on a unit circle z equal to e raised to j omega equal to 1. So this is how sampling is done. X cap e raised to j omega at omega equal to 2 pi k by n. So we are sampling it in the frequency domain at interval omega equal to 2 pi k by n, and that is equal to summation from n from minus infinity to plus infinity x cap n. X cap n is the appended sequence. Now x cap e raised to j omega is the DTFT of the appended sequence x cap n. Okay, so hope you got all these terms. Then e raised to j omega n at omega equal to 2 pi k by n. Again summation from n from minus infinity to plus infinity, the appended sequence x cap n e raised to minus j 2 pi k n by n. Again that is equal to summation from n equal to 0 to n minus 1 x cap n e raised to minus j 2 pi k n by n. Again that's equal to summation over n equal to 0 to n minus 1 x of n, that is the original sequence, e raised to minus j 2 pi k n by n, and that is equal to x of k. So we started with a DTFT. X cap e raised to j omega was the DTFT, and finally we reached x of k, which is actually DFT. So this is how DFT is developed from DTFT. So from the DTFT x cap e raised to j omega we obtain x of k, which is DFT. So this is how DFT and DTFT are related, or this is how DFT is derived from DTFT. So this particular sentence is very important. That is, this here it is a proof how it is derived, and everything they are summarized in this particular paragraph. That is, when the DTFT is sampled at uniform intervals in frequency domain, then the original sequence x of n in time domain will get repeated, and then it will be shifted by all multiples of n. Finally, it will overlap and get added to give you the DTFT in time domain. So suppose that if you have an original sequence x of n, we need to find its DTFT first, and that once the DTFT of the original sequence x of n is obtained, that DTFT will be sampled at uniform intervals in frequency domain. And once it is, if we are doing this, that is, once the sampling is performed, what happens to the original sequence x of n is that that original sequence will get repeated in the time domain, and then it will get shifted by multiples of n. Finally, it will get overlap, and then it will get added to get the DFT of the corresponding signal in the time domain. So first of all, repetition, then shifting, then overlapping, then adding. So this is how DFT is developed from DTFT. So this particular paragraph is very important. Now here this overlapping adding does nothing. Why? Because the appended sequence actually it is 0 outside the interval n equal to 0 to n minus 1. Okay, so what actually we get after extending it towards left and right is that we just obtain the original sequence x of n. So just remember this sentence and also the derivation part. Okay, no, that is enough for your from your exam point of view. But if it is asked for a long answer and all, you can add this also. This is just an explanation of sampling the DTFT. That is how sampling is performed. That is just an additional writing that you can do. The above one is enough, and if it is asked for more question, a more mark or long answer type question and all, you can add this also, just for more explanation. Okay, so if you are interested, you can go through this also. I will just read. That is, this is similar to what I have already explained. Okay, consider a discrete time signal x of n defined in the interval 0 to n minus 1, and we are let x cap e raised to j omega be the DTFT, and you are sampling it in multiples of 1 by n. So once the sampling is done, what happens to the original sequence x of n in time domain? I already said it gets repeated, and then the sampling at the rate of n samples per period will cause x of n to get repeated, and for every successive samples the repeated pattern will have information about x of n. Thus every time a DTFT is sampled, we get a discrete periodic time signal in time domain. So sampling is performed in time domain, and the repetition, the overlapping, the addition, the shifting, everything will be done in time domain. So this is how it is performed. This actually shows multiplying this DTFT by an impulse train here, and here these are the resulting samples that we obtain in frequency domain. So here, since there are n samples in the interval, the spacing of impulses will be 1 by n, and this actually results in the convolution in a time domain impulse train where the impulses are apart by a distance of n. So here this is how sampling is done. The spacing between the samples is 1 by n, whereas the impulses are separated by a distance of capital N. N is actually the length of the sequence. Now the time domain signal, the resulting signal is given here, and so this actually shows that sampling DTFT causes repetition of samples in time domain. See here, it is time domain. Sampling is performed in frequency domain, and the repetition and all is taking place in time domain. So the sampled version of DTFT is known as DFT, or discrete Fourier transform. Here frequency is discrete or sampled, whereas DTFT is discrete in time and continuous in frequency. So in short, we can say that DFTs are samples of DTFTs, or DFT is a sampled version of DTFT. So this is how we develop a DFT from DTFT. So you have a signal. First of all, you take the DTFT, then you are will you be sampling that DTFT in frequency domain at regular intervals. Then after that, so when you do for each sampling, correspondingly in the time domain, what happens to the original sequence? That original sequence x of n will get repeated, it will get shifted by all multiples of n, and then it will get overlap, and then finally it will get added to give you the corresponding DFT. So this is the theory as well as the explanation behind the development of DFT from DTFT. Okay, that's all for now. Thank you.